Hey guys, I wanted to go over the integral test because we didn't get to it the other day in class, and then this way I think you'll be able to do some homework problems about it this weekend. Okay, so let's talk briefly about two different kinds of, or two different things that are very, very related. Okay, so the first thing that we're going to talk about, I do not want to be in that color. The first thing that we're going to talk about is let's talk about the sum from 1 up to infinity, so the infinite sum, or the series of 1 over, not x, 1 over k, right? So we know, right, this thing's really 1 over 1 plus 1 over 2 plus 1 over 3 plus dot, 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 right? And let's talk about this guy. We'll call this A, okay? And then let's talk about B. B, we'll talk about the integral from 1 to infinity of 1 over x dx. And let's talk about how these things are related. Okay? So let's visualize here. Let's visualize the graph of 1 over x. So let's say maybe this will be 1. Right, so here we have some point here, right? It's going to go up this way. It's going to come down this way. You know, maybe we have points like this is a half here. This is 2 comma a half, and this is, you know, maybe 3 comma a third, and so on. Right? Okay. And we know that the area that B here, that B in blue is going to be, you know, this area underneath this curve going all the way out here, right? And we've seen that this particular integral, remember, if you want to remember this thing, right, this, we said this was the limit of b going to infinity of the integral from 1 to b of 1 over x dx. And we said, oh, that thing goes off to infinity. It diverges, right? It goes off to infinity because this becomes the ln of b. As b goes close to infinity, the ln of b also approaches infinity, albeit very slowly, but it does. So we know that this expression is this highlighted area. Let's talk about this expression, and maybe we can see that visually. Maybe we use green for A. Maybe we can see what that would be visually. So let's try to illustrate it. Let's try to illustrate it with some boxes. So the first term is 1, and I think you'll agree that this green box I'm drawing, has area 1, right? This has area 1, right? The green box area equals 1. This green box has area a half, and this looks like a left Riemann sum. You're right? And this area equals a third, right? And we see that these two things are very, very related. And we could also establish, right, that the blue area for this guy, right, and the green area are related, right? They're very related, and that you know, for this instance, the blue area is going to be less than or equal to the green area. But it turns out that actually, you know, we can sort of finagle our way around that, and that doesn't actually really matter. That we could just as easily count these areas. Do I have another color that I can use? This is going to let me pick. There we go. If I wanted to, I could sort of ignore the first term, right, and use these red areas for the right Riemann sum, and that's going to actually have the same result, okay? So we could also say, if I use the right Riemann sum and sort of ignored that first term, or we, you know, drew the first term over here, it doesn't matter, right? Whatever we do, we could say that the red area is less than the blue area, right? The red area is going to be less than the blue area. Okay, the red area is less than or equal to the blue area, which is less than or equal to the green area. Okay, so we could have either of these things, and that's fine. Okay, we can talk about how we sort of are squeezing the blue area in between, but the main takeaway here is that if I can show that a sequence or a series, right, an infinite series, right, this guy over here, part A, and part B share values at every integer, right, then they are very, very closely related, and that they'll either both converge or they will both diverge. Okay, so if we have some sequence, right? If we have some sequence, and then we take the sum of it. So if this guy is a series, and then we're gonna add some caveats here because we're gonna need to deal with only specific types, just like with our geometric series. We could only deal with things that could be modeled a certain way, right? Like a times r to the k minus 1. Here, we're going to only deal with a series with only positive terms, okay? And, right, so if this is only positive terms, and f is some function that is decreasing and continuous. Decreasing and continuous. Okay, we'll talk about sort of why those are critical in class. Okay, we'll say from a to infinity, from a to some a to positive infinity, such that a sub k equals f of k. What that means is, right, that this function, while this function is defined everywhere, right, this sequence here only has terms at every integer, right? So there's a first term, a second term, a third term. There's no such thing as like the term 2.5, right? There's only, it's discretely defined at every integer from 1 to infinity. This function is defined everywhere. Like we could say what's f of 1.5, but we don't care, right? But all I care is that on all the integer values that my function, right, at 1 over x over here, 1 over x, this guy, right, this guy here, 1 over, like if k were 4, right, the fourth term over here is 1 over 4, the fourth term over here is 1 over 4. That's what we're after, right? The fourth term of both of them is the same. Okay, so if we have a series with only positive terms and f is some function that's decreasing and continuous, such that we have this idea that they're the same everywhere, right? Then we can talk about these two things that we sort of sketched up there, the infinite series, and this improper integral from a to infinity either both converge or both diverge. Okay, so what on earth does that mean? Either they both converge or they both diverge. This is going to be very, very helpful for us, okay? Because now we can look at something that looks somewhat scary, and we can use an improper integral, like the unit we just finished, to sort of decide whether it converges or diverges. All we have to do is sort of match the sequence, or the series, to a function. And that turns out to be kind of easy, right? Because all we need to do is write a rule for this guy. If we can write a rule for it, then we can set that function equal to that, and we can go from there. Okay, so we have to be very, very careful about indexing, right? That we make sure that we index properly, and that we know that our first term is their first term, and so on. But once we do that, we can really do a whole lot of things. Okay, so I'm actually gonna do something that I think I was gonna ask you to do for homework. Let's do number 9 from the book together. Okay, so it says determine if let's do this guy here. Determine if this thing converges. Okay, so we can list these terms, right? This series is really 1 over 7 plus 1 over 8 plus 1 over 9 plus all of these guys, right? All of these guys. Okay, well, all I need to do is come up with a function where my f of 1 is going to be this, f of 2 is going to be that, and f of 3 is going to be that. And this is as easy as just saying, oh, well, my f of x here is just going to be 1 over x plus 6. X plus 6. Okay, and then we see that this series and this integral are very, very related, right? This is simply summing up the area underneath that curve, 1 over x plus 6. And this is sort of discretely taking a Riemann sum, sort of saying, oh, 1 over k plus 6 times with width of 1, right? But we see that they're going to match every value just like our picture up here. Just like our picture up there, they're going to match every single value. So I'm going to be left with these two things. So all I need to do is evaluate. I can ignore this series here, and I can say, does this converge or diverge? That's the new goal, right? And we know how to take that, okay? We don't know so much how to deal with this, but we know how to take this. I should have mentioned before we get into this, we have to just think very briefly about our function here, right? So is this thing continuous? Yes, it only has a discontinuity at -6, which is not something we're worried about because we're going to start at 1. And is it decreasing forever? Also, yes, right? This will also be decreasing forever. So it meets both of these criteria up here. So we're good. And lastly, right, this original series does only have positive terms. So we can use this set of tests, or we can use the integral test to decide whether something converges or diverges, right? We need all three of these criteria here, 1, 2, and 3 in order to use it, okay? Just like we needed a geometric series to use the geometric series test. Okay, so does this thing converge or diverge? We are now trying to evaluate this integral, right? Well, fortunately for us, this is kind of easy, right? This is just a limit as b goes to infinity. No need to do anything fancy here, right? This is just the ln of x plus 6 evaluated at 1 and b, right? So that, of course, is the limit as b goes to infinity of ln b plus 6 minus ln 1. Okay, I know we all know what this is, but it doesn't even matter what that is, right? Because this thing is going off to infinity, and this thing is certainly discrete. So this thing does not exist, and it diverges, right? The limit doesn't exist, so this thing diverges. So therefore, so does that series, right? So we can determine that series diverges because of that. Okay, so I know that there are probably going to be questions. I would like you to sort of work your way through a couple of these guys, and we'll see sort of where we're at on Monday. There's no quiz on Monday either. All right, have a great 3 or I guess 2.5 day weekend at this point.